right? Question one in the assignment is this. You're going to see that this talk about three variable situation, right? And they ask you to find the values of k. Of course, if you want to find the values of k, integral. So f of x dot, the x, the z, okay, or the y, the z, they must be equal to 1. So this is a clue. That is what, any question on that, on how to find your k? So this is what you're going to do. The first question asking you to find the values of k. So we're actually going to use triple integral for that. And if you look at the second question, it said determine the marginal function of x, y, and z. So you basically want to get f of x, right? If you want to get f of x, it means you actually need to integrate this guy, okay, with the, if you take a look at what I have here, before you can get if you want to get f of x, it means you're basically going to have to integral. What are the variable you are not interested in? You're looking for x, right? You're not interested in y and z, right? Then you're going to, does that make sense? That's super easy, right? So if you want to do the f of y, you're going to go the same way, right? You're going to go the same way. So y, you're not interested in x and z, right? So x, z. So take a look at that. So you're not interested in that. So the similarly f of z, integral f of that z, okay, the x, the y. Any question on how to get the marginal? Any question on that? Okay, so that is what you're going to do to get the marginal. Now take a look at the other question. Determine the joint marginal distribution of f of x. Now you know that now. Now another question is asking you, situation where you got three variables, two variable become marginal. Now you want to find the f of x, y, right? Okay, you are interested in this guy. Okay, it means this guy will be, you're going to integrate that with respect to the variable you are not interested in. Any question? And the range of z is what you're going to use. Don't forget. Okay. Of course, you know what to do. Here, as you can see, find the joint marginal distribution of all of that. Okay. So any question on that? And don't forget, what if you're giving a question? What is the f of what is the distribution of z given xy? What if they ask you this conditional, right? What are you going to have? Ratio of the joints, right? Divided by what? You see that? This guy here, you're going to find it from here. Whatever you get, you're going to use. So we can ask you several questions. Take note. Okay, so, and the last question too that I also in the assignment says, okay, this is like asking you to get the expectation of the product. Of course, if you basically, if you want to find the expectation, if you want to find the expectation of the product, the expectation of x, y, z, right? Of course, you're basically going to have three integrals, integral, x, y, z, then the function, the x, the y, the z. Does that make sense? Okay, so this is what you basically, so that is how that goes. because I realized that I needed to review question 1 and question 2 of the assignment 6 with you. So which is what I've done now. Okay, so I want to go into today's topic, this week topic. Like I said, this week topic going to focus on chapter 5 in the textbook. This way we want to focus on, discrete probability distribution. Discrete probability distribution. We got a lot of distribution in a discrete probability distribution. We got the Bernoulli, binomial, multinomial, hypergeometric Poisson distribution. Okay. We have the negative binomial geometric as well. So that, of course, that will be our focus this week. The same way we have, region in the United States. Some are in the east, some are in the Midwest, some are in the West. We also have different kinds of probability distribution. Of course, if I talk about Midwest, I'm talking about the Illinois, or the Michigan, the Wisconsin, the Minnesota. So just like if I'm talking about discrete probability distribution, that's as a family. Okay, that's what I mean. A variable could be a discrete or a random variable, but maybe from a Bernoulli distribution, maybe from binomial, even though it's a discrete. Okay, so and that is what we want to study this week. Now, I'm actually going to start with Bernoulli. Random variable. So, in a Bernoulli random variable, we got to, when we perform experiments, how many times? Once. And we got two possible nature. There are two possible outcome. It's either we record failure or success. Does that make sense? So, which means in our sample space, when I try once, when the number of my trial is 1, it's either I see success or failure. So, because we got two events in the sample space, we're basically going to have two probability, because every event in the sample space has its corresponding probability. Nobody goes into research with an empty mind. Nobody go into experiments with an empty mind. If a business woman or man go into business, you know what he or she has in mind? Profit. But you know what? There are two possibilities that could happen. One of them is going to happen. It's either he or she record profit or loss. Okay. Now the probability of recording failure is going to be 1 minus P, and the probability of success is going to basically going to be P. Okay. I wanted to take note of that. Now, this is just an example of a Bernoulli process. The Bernoulli process must possess the following property. Number 1, the experiment consists of a repeated trial. Now, let me tell you this. I can go from Bernoulli to binomial. When the numbers of trial equal to 1, and I got two possible nature or outcome, we call that Bernoulli. But when the numbers of trial is more than 1, the repeated Bernoulli process becomes binomial. Does that make sense? Repeated Bernoulli process become binomial. And in this trial result in an outcome that may be classified as a success or failure. Do you know when we test our patients for COVID, okay, from one patient to the other, if I know the prevalence of COVID in the population, right? If I know the prevalence rate of COVID in the population, right? The probability of catching COVID, okay, is going to be the same from person to person. That makes sense, right? And if I go from person number 1 and I test, it's either the person has COVID or not. Go to the next person, it's either the person has COVID or not. So that's what we mean. And the probability of success remained constant. That's what I said. The probability of having that characteristics of interest remain the same from person to person. That's exactly what we mean. Then the repeated trial have to be independent. These individuals, the fact that this individual has COVID does not mean the other one is going to have. But that assumption may not be true all the time. I'm going to tell you why it may not be independent. You remember during the COVID time, if a member of a family has a COVID, what is going to happen to other members that live in the same household? They're basically going to pay attention on them, right? That there is high probability. Now, in that kind of situation, independent may not work anymore. Does that make sense? Okay, so I just wanted to take note of that. Now, consider now what I'm just, if you take a look at this now, when you or consider the set of Bernoulli trials, where three items are selected at random, okay, from a manufacturing process, inspected and classified as effective or not effective. Let me tell you this, because there's always going to be a variation in life. Whatever we do, variation exists. In the production process, right? I actually want to believe that every company that are into production should have a quality control office. The quality control officer is just they have the ability to catch defective. There's always going to be defective, no matter how we try. Okay, even using the same machine for repeated process, there's basically going to be defective. So which means what we classify, what we produce is going to be going to comprise of defective and non-defective. Does that make sense, right? Okay, so a defective item is designated a success. You're going to say, oh my God, a defective item designated a success. What does that mean? Okay, success in this case means that is our characteristics of interest. Does that make sense? That's what we mean by success. Success, okay, actually that we're referring to here means characteristics of interest, okay, what we're focusing on. You get what I mean? So that's why you call that success. Okay, so the number of successes is a random variable. Why is the number of successes a random variable? If I produce 3 items, it's going to be a random variable because the numbers of defective I'm actually going to have from the 3 items could be 0. We could have a situation where we produce 3 and no defective at all. And there could be a possibility that we could have 1 defective or 2 defective, or even all of them are defective. And that is why it's going to be a random variable. That's why it's going to be 0, 1, 2, 3. Does that make sense? Now, if I actually produce 3 items, before we need to, 4 of us, understand what is a sample space. Okay, we need to, 4 of us, understand what the sample space is. I know the possibility, defective or not, right? Which is going to be 2 raised to power n. Okay, numbers of items, then I know I'm basically going to have 8. Okay, of course, if you make use of tree diagram, okay, if I use n to denote non-defective and I use d to denote defective, and I when I produce 1 item, the sample space is going to be 2, right? That would be 2 raised to power 1, 2, right? If I produce 2 items, you know what's going to happen? N, D, okay, the sample space is going to be 4. It's going to be N, D, D, N, D, D. Okay, but what if I produce 3 items? This guy is going to go to ND, or ND. I'm actually going to have ND, and I'm actually going to have ND. If you take a look at all of that, the possibility, that is what you see in the table. Does that make sense? And there are going to be 8 of them. And of course, we need to define our X. X is the numbers of defective, in the first one. S equal to 0, N means the 3 items are non-defective. Okay, in that situation, S will be 0. Don't forget, what does your X represent? The numbers of defective. Okay, so now what are we doing now? We want to find the probability. Let's say, for instance, you basically want to find the probability of NDN. Or what is the meaning of NDN? The NDN is more or less like, okay, out of the 3 items, it is only 1 that is defective. Okay, so, and of course, don't forget, we are actually assuming independent, right? So what is the probability of the joint? of NDN is basically going to be the product of the marginals, and that is how we got that. And do you know from that table, we can create a probability distribution, okay, where we're going to have x star from 0 to 3, and of course, we can actually find, what is it? You know, the 9/64 that you see, okay, is just one of the inputs here. 1/64 is just, what is the probability of x equal to, 2? What is x, equal to, as you can see there, when s equal to 2, you have that. When s equal to 0, you can find when s equal to 1, okay, and so on, like that, okay? So take a look at that. Now, we want to go from Bernoulli now to binomial. But before we go from Bernoulli to binomial, you need to first understand Bernoulli before you go to binomial, okay? Binomial is so many Bernoulli, okay? Now, if I want to talk about situation where I got a repeated trials, the number of trials is more than 1, okay, then I'm going to be talking about binomial. But there's something I need you to understand. In Bernoulli, the mean of success in Bernoulli is P. The variance is, we can figure out variance to be P into 1 minus P. Okay, we're going to, now, let's now come to binomial now, where we have more than 1 trial. Okay, go ahead. Exactly. Bernoulli only has 1 trial, n equal to 1. But when I repeat Bernoulli now more than once, it becomes binomial. Does that make sense? Now, that's a very good question. Now, because of that, I'm going to do this now, and you will see the generalization. For Bernoulli, okay, the f of s in Bernoulli is this guy here, where x start from 0 and stop at 1. What is P? The probability of success. What is X? Number of success. The probability of success will carry number of success. What is Q? The probability of failure. How many failure if you try once? If n equal to 1, if you try once, and X is the number of success, what would be the number of failure? That would be 1 minus X. That is why you say 1 minus X. Do you see that now? So Q, the probability of failure, is carrying number of failure. The probability of success is carrying number of success. Now, if I want to go from n equal to, from more than 1, okay, if I want to go from n equal to 1 to more than 1, then I'm going to come here. It becomes binomial. Look at that. What do you see? What is the difference between the formula here and the formula here? You introduce a combinatorial analysis. Look at that. N combination X. But there's something I want you to do. Plug in 1 here. When you plug in 1 here, where you coming to? You're coming back here. If you plug in 1 here, 1 combination X. Basically going to be 1. And plug in 1 here, you're going to have P raised to power X and Q raised to power 1 minus X, which is going to be this guy here. Therefore, what is the takeaway? Binomial is a generalization of Bernoulli. Why Bernoulli is a special form of binomial. Does that make sense? The only difference between the two, okay, is for Bernoulli, the number of trial equal to 1. For binomial, it's more than 1. Does that make sense? Okay, that's what we have. Now, where does the name binomial come from? Of course, I know you've heard about binomial expansion before in mathematics. Binomial expansion. Has anybody heard about Pascal triangular formula in mathematics? Yeah, Pascal triangular formula. Good job. Now, I want to talk about P and Q. Of course, in both Bernoulli and binomial, we actually focus on P and Q. What is P? The probability of success, right? What is Q? the probability of failure. Don't forget, P plus Q must be equal to 1. The probability, the events of success and the events of failure are mutually exclusive. You know that, right? Okay. They are mutually exclusive. Okay. If events are mutually exclusive, then you expect their probability to add it up to 1. Okay. So because of that, in some textbook, you're basically going to see Q to be 1 minus P. Does that make sense? Q can be 1 minus P. Now, take a look at what I'm displaying now. If I have Q plus P raised to power n, okay, and I want to investigate that using the binomial expansion, I'm going to have n combination 0, Q raised to power 0. Where is P? Oh, P is counting 0 at the beginning. Anything raised to power 0 is 1. That is the reason why it's not showing. Then you're going to get to a point, the last time of that is going to be P raised to power n, where is Q? Because Q is counting 0, and anything raised to power 0 is basically going to be 1. In the end, what do we have? Everything here is going to add it up to 1. Okay, of course, we know P plus Q is 1. 1 is power n is basically going to be 1. Okay, take note of that. Okay, now we want to talk about the properties of binomial now. If a random variable x follow binomial distribution, what does it mean? What is the variance? Okay, now if I want to know the mean and I want to know the variance, then I need to first know what is the mean and variance of a Bernoulli. I'm going to say that again. I want to know the mean and variance of a binomial. The moment I know the mean and variance of a Bernoulli, I can figure that out. Now, let me tell you, when I have, I can ask you to show this. Let's take a look at this. How do we find the mean of x here for Bernoulli? Don't forget, Bernoulli is a discrete random variable, right? I mean, it's a discrete probability distribution, right? It's going to be summation x, okay, f of x, right? Don't forget, right? And x starts from 0 to 1 for Bernoulli, right? What do we want to do? We want to find the expected value of x, right? Okay, now when you're going to start from 0, so P raised to power 0, Q raised to power 1 minus 0, plus P raised to power 1, Q raised to power 1 minus 1. Okay, now what happened here? Okay, so when you take a look at and don't forget about x. Okay, x equal to 0 here, s equal to 1. Okay, because of this 0, everything there is basically going to be 0. I'm actually going to have, what do I have? What does it mean? What is the mean of a Bernoulli? P. That is how to show the mean of a Bernoulli is P. And you know what? If the mean of a Bernoulli is P, what will be the mean of a binomial? That will be NP. Because binomial is many Bernoulli. Okay, now, the same way here, if you want to find the variance, you're basically going to use this guy. Don't forget what we've done before. Okay, if you follow what we've done before, this is basically going to give you PQ. The variance is going to give you PQ. Now, if I now want to generalize, I want to go to binomial now. What I'm just going to do is to pull n and put n here. Take a look at what is on the board. What is the variance? What is the mean of a Bernoulli now? NP. What is the variance is of a binomial now? NPQ. And do you know I can go from here back to here when the numbers of triad equal to 1? What happened? When n equal to 1, the mean it become P, and when n equal to 1, the variance become PQ. Any question on the two? Any question? Any question? Okay, that is how that's how we solve that. So that's why we said if I know the mean of a Bernoulli, if I now had Bernoulli P plus P plus P plus P in n way, That becomes NP, right? Which is binomial binomial. And if I know the variance of Bernoulli to be PQ, right? If I now had PQ plus PQ plus PQ in n ways, that was going to be NPQ. Okay, so that is just different. Any question? Do you know what I'm targeting now? That is possible, right? The mean, the median, the maximum, the minimum of the midterm 2 can be 100. You know that, right? Okay, if you don't understand what we're doing now, please ask question. We are counting down again to the midterm 2. Okay, let's go to the example now. The probability that a patient recovers. Let me tell you this. Why is this binomial? Because a patient may recover or not. Binomial is a distribution that is characterized by dichotomous outcome. What do I mean by dichotomous outcome? Outcome that can be this or that, recovers or not. In economy, economy could go into recession or not. That particular guy may win election or not. Does that make sense? That's a binomial. Okay, now I'll recover from a rare blood disease is 0.4. You know that 0.4 is a prevalence. That's a P. Okay, if 15 people are known to have contracted this disease, what is the probability? A, at least 10 survive. B, 3 to 8 survive. C, exactly 5 survive. Now, at least 10 survive. Okay, that means you want to figure out the probability of S greater or equal to 10. At least 10 means 10 or more. Does that make sense? Okay, so 10 or more. Okay, it means I can also write that as 1 minus the probability of X less than 10. And the probability of S less than 10, of course, in exam, I'm actually going to allow you to use a calculator or, to be able to figure that out if you don't want to use a formula approach. All what you just need to do in the calculator is to supply what is sample size and what is actually your P, which is 0.4, because, and of course, I'm going to allow you to use a binomial table. There's a binomial table, right? Have anybody asked about statistical table? As part of the statistical table, there's a binomial table. I'm actually going to bring one to this class on Wednesday, okay, for you to be able to see. Or maybe I can share that with you. I think I'm going to share that with you maybe tonight. Okay, so between 3 and 8, that is a way to solve for exactly 5. That is a way. But manually, the only thing you're basically going to do is to apply, the formula here. Okay, that may actually take forever. Okay, so I put another example. Any question with the way binomial work? Is there anyone want to ask question before I move to something else? Is there anyone? Okay, if you're good, I'm going to go into another important distribution that we call multinomial. What is the difference between binomial and multinomial? Okay, binomial focus on two possible outcomes. Why multinomial focuses on more than 2 possible outcomes? Does that make sense? That is the difference between the two. I'm going to say that again. Why binomial focuses on 2 possible outcomes? Multinomial, on the other hand, focuses on more than 2 possible outcomes. Does that make sense? Now, let me differentiate again. What is the difference between Bernoulli, binomial, multinomial? The difference between Bernoulli and binomial is that the two of them focus on the similarity between them. The two of them focus on 2 possible outcomes, except that Bernoulli is used for 1 trial, while binomial, many trials. Trial more than 1. But what is now the difference between binomial and multinomial now? Oh, binomial focus on two categories, two possible outcomes. But why? Multinomial. Look at the word multi. It means we got more than two outcomes. Does that make sense? Now, mathematically speaking now, when we have more than two possible outcomes, we're basically going to have more than two events. Event E1, E2 up to EK. And all these events, they're basically going to have their respective probability. You know, in life, every event has its corresponding probability. And that's why E1, we have a probability of P1. E2 is going to have a probability, so on like that. Now, if I now want to write, how do I actually write multinomial? I need to be able to generalize binomial. Okay. Now, you remember we did a combinatorial analysis the other time, right? Where we were, I remember under permutation, when we're dealing with a permutation with distinguishable characteristics. Take a look at that. I'm actually going to have n combination x1, x2 up to sk. And I'm also going to have k numbers of probability because I have k numbers of events. So this is the formula. And in such a way that when I sum x, it should give me n. And when I sum pi, it should give me 1. So which means under the binomial expansion, initially, you know, we were considering p plus q raised to power n, but here now it's basically going to be p1 plus p2 up to pk raised to power n. That's what we call the multinomial. This is another way to put it. This is another way to put that. You remember the first part, n factorial divided by, we've done that on that distinguishable permutation, right? Do you remember that? Because the n was partitioned into different category. Take a look at that. With their corresponding probability. Okay, this is another way to put that. That guy can be written as that. You see the one in the parentheses? Okay, I want you to take note of that. Now, if I want to do some mathematics now, okay, I want to do some mathematics now, so I just want to tell the world, I basically want to prove that, you know, the n factorial divided by x1 factorial, s2 factorial to sk factorial, the beginning is that, where I actually want to select x1 from n. And if I want to select x2 now, do I see have my complete n? No. Hello? Do you see the first one? N combination x1, right? I'm selecting x1 from n, right? If I now want, look at the second one. If I want to select x2, do I see have my complete n? No. I have to tell the world that I've already taken x1. That's why you see n minus x1. If I now want to select x3, I'm no longer selecting S3 from n, but I'm selecting S3 from n minus x1 minus x2. Does that make sense? Now that goes all the way, and in the end we have that. So I'm just trying to tell you how we are able to get that in place. Okay, now let's look at the example of multinomial now. The example is basically going to interest you. Okay, let's go back to stock. Okay. I think I got the news of a particular bank failing, right, in the United States. Or normally listen to news. Okay, a lot of things are going on, so watch the news. Now let's talk about stock now. Okay, suppose that an earnings, okay, announcement has 3 possible outcomes. Look at that, 3 possible outcomes. Then my mind should be thinking of multinomial. It didn't say 2 possible, right? Does that make sense? 3 possible? That should be multinomial. Okay, now let's look at the outcome now. One, positive stock price reaction, and the state of nature having that there's a 30% chance of having a positive stock price reaction, and 50% chance of no stock price reaction, and a 20% chance of negative stock price reaction. This is market reality. Okay, what is the state of nature now? 100%, 30 plus 50 plus 20, right? What does that give? 100%. Take a look at that. Okay, Now, which means from what we're given now, we already know what our P1 is. We know what our P2 is. We know what our P3 is. Now, suppose today, four different firms, release any announcement because there are 4 firms. It means N is going to be equal to 4. Does that make sense? Okay. Now, let X, you need to define what is your X, right? Let X represent the number that results in a positive stock price reaction. I know that is what they want. Oh, so that we can jubilate, right? The positive one. And let Y represent the number that results in no reaction, and Z, the number of results in a negative reaction. What do we have here? X, Y, Z. Do you see that now? X, Y, Z, where each of these actually represent different outcome, right? Okay, now find the distribution of X, Y, and Z. Compute the probability of X plus Y greater or equal to Z. Before you'll be able to, conduct inference, because statistical inference is finding the probability, then you need to be able to use the right probability distribution. Now, when you take a look at the first question, it says find the distribution. Of course, the distribution of X, Y, and Z will be multinomial. All what I'm just going to do is to plug in the values in the multinomial. Look at what I have now. What have I just done? What am I using now? I'm using N. I'm actually, I'm using, what is my N? My N is the numbers of firm. Then I'm going to go from X1 to X3. Okay, yeah, this is a general one. Now I'm going to go from P1 to P3. I've already plugged in the values. Is there anyone who doesn't understand P, X, Y, Z, how we got it to be that? Is there anyone? We just plug in the values given into the multinomial distribution. Does that make sense? Okay, any question? Oh, go ahead. Oh, the P into X. That is the P1. Do you see the formula? P1 raised to power X, and that very P1, P2, P3, the probability of the state of nature has already been given. Do you see that up there? 30%, 50%, and 20. That's already been given. Okay, that's a good question. And from there, we got P1, P2, P3 to be that. Okay, now, this is what we have. But the question now is, and don't also forget, the summation of the xi must be equal to n, numbers of trial. And that is the reason why we said, look at that, x plus y plus z must be what? 4. Do you understand that? We said that here. I'm going to show you where we actually, okay, do you see it? Summation xi equal to n, right? So when I had all the different outcomes, it should be equal to the numbers of firm this time around. Okay, and that's exactly what we have now. Now, where you have a serious work, right? They ask you to find the probability of x plus y greater or equal to z. Then you're actually going to use this here, and you're going to construct a probability. You're going to construct a table. Do you see this table? This is a table of 3 by, look at that. The first column is for X. The second column is for Y. And the other column is for what? For Z. Look at that. So we generate, what are we? This is the probability of X, Y, Z. The whole of it. This is like a joint. Okay. Okay, if you take a look at the first one, here, if X equal to 0, Y equal to 0, and Z equal to 0, how do we get that? You're basically going to come to the formula where x equal to 0, y equal to 0, z equal to 0. You determine that. When you vary different kinds of the values of x, the values of y, you're basically going to have this guy. Now, the moment you have this guy now, you can now solve the probability of x plus y greater or equal to z. When I add x to y, right, which is going to be 0 plus 0, okay, greater or equal to z, okay, then I can compute that. Okay, I wanted to go over that. Now I'm quickly going to go, and of course, at the end of the day, when I add up, I'm actually going to have that. You can go through that. Now, the last example before I go. How many more minutes do I have? like 5 more minutes, right? Okay. Now the complexity of we're talking about airport now. I feel I'm thinking about vacation now, right? Is in my mind. Snow should go, right? Okay. Now the complexity of arrivals and departures of planes at an airport is such that the computer simulation is often used to model the ideal conditions for a certain airport with three runways. That is multinomial, not two, right? Three runways, right? Okay. Now, three runways. It is known that in the ideal setting, the following are the probability that individual runway are assessed by a randomly arriving commercial jet. Okay, the runway 1, runway 2, runway 3, you already have the probability based on what has happened before. Does that make sense? Now, what is the probability that 6 randomly arriving planes? I think I had a news that 2 planes arriving at a time. I don't know whether you have that news too. Okay, so that they don't want that to happen where 2 planes they're going to use the same runway at a time. But right now, what is the probability that 6 randomly arriving planes are distributed in the following version? Runway 1, 2 planes make use of runway 1. Runway 2, 1 plane. Runway 3, 3 planes. If you add all those planes together, 2 plus 1 plus 3, that becomes 6, right? So which means so now using the multinomial now, we can find the joint probability of that. The joint probability that 2 planes will use, if 6 planes arrive, the joint probability that 2 planes will use runway 1, 1 plane will use runway 2, and 3 planes will use runway 3, which means we basically want to find the probability of the joint. Okay, if I put X, Y, Z, the probability of S equal to 2, comma, Y equal to 1, and Z equal to 3. What am I going to do? I'm actually going to plug in all the values that I'm giving in the multinomial probability distribution. So can you see that? N is 6, right? 2, 1, 3, look at that. Any question? Without I got that, the probability is 0.1127. That is the probability that, if 6 planes arrive randomly, 2 we actually use runway 1, 1 we use runway 2, and 3 we use runway 3. Any question? Do you enjoy multinomial? Easy. Okay, this is where I'm actually going to stop. What do we have next? Oh, we're going to hypergeometric distribution next. But because I see I have time, what is the connection between the hypergeometric and the distribution we have done today? The connection is that the Bernoulli, binomial, multinomial, we sample with replacement. But hypergeometric, we sample without replacement. That is the difference between them. So we're going to start hypergeometric on Wednesday. So hypergeometric also talk about categories of outcome, except that the difference between hypergeometric that we're going to start on Wednesday and the binomial and the multinomial. Let me tell you this, we also have multi-hypergeometric. Okay, when I say hypergeometric, maybe I'm talking about 2 possible outcomes, but the sampling is done without replacements. And I can also have multi-hypergeometric, where I got more than 2 possible outcomes, and the sampling is done without replacement. But for the Bernoulli, binomial, multinomial, then the sampling is done with replacement. Any question? Interesting topic, right? Any question? Okay, for those of you who have collected your booklet, if you take a look at that and I made a mistake in the totaling your score, please let me know, okay, on Wednesday. So, bye for now, everyone. And you should expect a homework discussion tonight. I'm actually, yeah, go ahead. Yeah, you can keep it, yeah. And the solution will be, I think I'm going to publish the solution probably tomorrow, so that in case you can compare yours with the solution. Okay, bye for now, everyone.